Yeah, I think we are live now. I see people joining in. Awesome. Hey, hi everyone. A very warm welcome to each one of you. Glad to see you all joining. I hope you all are healthy and safe from whichever the part of the world you are joining from. For those unattended, we at DeFi are a global data science community, which we started last year with the vision to democratize data science education. And in our constant endeavor for the same, we keep conducting regular boot camps, live sessions from industry experts, data challenges, and much more. Our today's session on automated image captioning is one such initiative, and our heartfelt thanks and gratitude to Aditya for agreeing to do this. I'm sure most of you would already know him, but for others, Aditya is a seasoned AI professional who is currently working at West Pharmaceuticals as the lead AI ML engineer. He comes with a rich experience of leading and managing global AI teams, building world-class AI products, and establishing AI practices at some of his past organizations as well as at West. Not just that, Aditya also devotes his time to mentor and teach people at Must Research Academy and loves to contribute back to the community through sessions like this. Without further ado, I'd like to bring him on and let him take over the session. Thank you, and over to you, Aditya.
Yeah, thanks, Yes. And a warm welcome to everyone for this session on automated image captioning using attention-based multimodal deep learning. So before we probably get started with the session, I would like to share a few points about myself. As Yash has mentioned, that I'm currently working as the lead AI/ML engineer in a 98-year-old pharmaceutical company called West Pharmaceutical Services. And I have the responsibility of leading and managing the global AI team over there and working on multiple AI products and platforms for West. So particularly in the data science domain, I'm well experienced around computer vision, time series analysis, natural language processing, and have worked on multiple initiatives and projects related to data science and AI in general, and even helped to establish the AI Center of Excellence at my current organization. And as Yash has mentioned, that I am also a researcher apart from my day job, and I work or kind of contribute at an NGO called Must Research, and I'm one of the faculty members over there. So again, like if anyone wants to reach out to me, feel free to reach out to me through my LinkedIn profile or through my website. And these are some of the organizations that I have been associated with. So I'm currently working at West, as I said, and previously I have worked in Microsoft and Intel. And apart from that, some of the initiatives I kind of do through Must Research. Okay. So for this particular session, these will be some of the key topics for discussion. I'm going to give a brief introduction of what exactly is multimodal learning and how do we deal with the multimodal dataset for a problem such as image captioning. But even before that, I'll try to give some exposure on the general idea of multimodal learning and what are the typical use cases in which dealing with multimodal data sets would be very important to build robust AI systems. Then I'm going to give some brief overview of the different techniques or different mechanisms involved in multimodal learning. But for this particular session, for the image captioning problem, we are going to focus on the technique of early fusion mechanism. Okay. Now, for the typical deep learning architectures, there are different styles, different flavors which are involved. For this particular multimodal learning, we are going to deal with an encoder-decoder architecture. So I'm going to give that overview of an encoder-decoder architecture as well, and why exactly do we need when we are dealing with a multimodal data set. And finally, this is one of my topics of key interest and research is on model interpretability. Now, as more and more organizations and different companies are adopting AI for their critical business making processes, that's where model interpretability is even much more important than it was before. So right now, like even if we have a very robust maybe machine learning or an AI model that can predict with high amount of accuracy or efficiency, but until and unless the model results are interpretable or something which is explainable and understandable for the business stakeholders, the results actually doesn't hold that much of value. So here, for a typical image captioning problem, I'm going to discuss about a technique of visual attention mechanism, which kind of makes the entire idea of this image captioning problem much more interpretable. And we can easily understand that why whatever the results that we are getting from the model is coming because of the, the typical functionality of the model. Okay. Now, another important point is on the model evaluation part. Now, as compared to other deep learning technique, the model evaluation metrics for this particular image captioning model would be a little different. So that's why I'm going to give some exposure about different types of model evaluation metrics, which one to go for, and why do we want to go for such a particular metric. Okay. So these are the key topics of discussion. Now, as I understand, like in this session, like we will have audience of different backgrounds, of different competency level. So I'll try to make this particular session as simple as possible so that anyone can understand. But if someone already has some exposure on some of the topics that I'll be discussing, and if you want to know something which is a little more at an advanced level, feel free to shoot me out on like those specific questions, maybe during the session, or even we can connect after the session and have a discussion on it. Okay. Now, let's start with the actual content of the particular session today. So what exactly is a multimodal learning when we talk about it, right? And typically, what is the role of deep learning in this particular perspective? So if we think about it, most of the real life problems that we solve or that we deal with may not be related to just one single modality. It may include a lot of combination of observation of different modalities. Say, for example, images, like when we talk about the vision, it can be related to a combination of the vision part as well as the speech part. When we talk about maybe something like a person recognition system, where like, let's say whenever as a human being, whenever we try to recognize a particular person, it is not always just the vision part that we consider. We consider both the vision as well as the speech part in terms of more importance. Sometimes we even consider other aspects, let's say related to the maybe the aura of it, the smell of it, or maybe the touch related sensation and so on. But typically for a person recognition system, most of the time we rely not only on our vision, but at the same time the auditory signals that we are able to capture, right? So that's why as a human being, our ability to recognize a particular person is much more robust as compared to a particular AI model or a particular bot, like robotic agent, right? And the main reason is, in most of the cases, these AI models or these robotic agents depend on only one modality. Like either it can be related to vision or it can be related to speech, right? Let's say if we talk about something like an a voice assistant like Amazon Alexa or maybe Google Home. So those devices mostly depend on the speech signals what it gets through. But because of its reliability on only one type of modality, sometimes some of these systems are not robust enough. And I'm sure like some of you might have even heard about these news where accidentally, Amazon Alexa ordered something which it was not intended to do just by randomly picking up signal from its external environment. And it was not relying on other modalities, because of which it captured those external signals and kind of made a decision based on the data that it was getting. But if we are able to make a particular system which not only depends on just one type of modality, but also, let's say, depends on other multiple modalities, and then collectively makes a decision, in those cases, the systems are much more robust, much more reliable. And for any practical or industrial use case, if we talk about, it is much more efficient and much more reliable in such cases. Okay. So that's where whenever we talk about building robust AI models, one thing we should always consider that whether if we go for only one type of modality, is it good enough? Or can we even consider different types of modality and have a much more robust combination model that can help us to get much more reliable and robust results? Okay, so that's where multimodal learning comes into picture. And this is just one example where person recognition systems, if it is converted or made to rely on multiple modalities, can give much better results. Okay. Now, I'll try to go a little more in details again, and some of the parts we have already discussed, that why multimodal, like especially when we talk about any human decision, it is a fusion of multiple modalities from aroma, touch, sound, speech, vision, and so on. But when we talk about representing an AI system, there are like different types of representations that can happen. And I'll going to connect this, like this particular learning that we will have over here with the one problem that we will be focusing on later. Okay. So when we talk about a multimodal system, there are different ways by which we can represent the key features of the systems. Okay. So let's say if I have two types of modality, one related to maybe text, one related to images. Now what I can do, I can just combine the entire data together, maybe vectorize it in some format that the raw data sets are converted into a numerical format, and then apply a certain, a CNN or maybe any kind of model architecture and create certain feature vectors out of it. So this is one example where we are combining data sets of different modalities and then creating a joint representation of it. It's actually known as joint representation. So the features that we create, or the feature vector that we finally obtain out of it, it considers both the modalities together, and it is a combined or a joint representation of the entire feature. Okay. Now another type of multimodal system, or in terms of representation that we have, it's called coordinated representation, where we generate, let's say, like features from one particular modality, let's say images, and we generate another set of feature from another type of modality, let's say the textual data, and then just combine both the features together. Okay, so that is an example of coordinated representation. Now again, like it depends on the particular type of problem, which style of representation that we want to adapt to. But in most cases, what I have observed, especially whenever multimodal system is kind of involved, coordinated representation is the go-to approach. But there are multiple scenarios in which joint representation can also be used. Okay. Now we talked about the representation approach, but there is also one type of mechanism which kind of decides the entire fusion approach. Okay. So when we talk about different fusion approaches, there is one typical type of approach which is called early fusion. When we have modality 1, we have modality 2, and then we pass both the features of those modalities into a training network, and then we will have a classifying layer which will finally help us to classify or come up with the exact result. Okay. Another type of technique, it's called late fusion technique, where we actually have the classifier before the final prediction that we want to do. So basically, it's like it will consider a separate network. It will have some sort of input. It will make a decision, and separately for the other modality or the second modality, it will again have a separate set of network. It will go through the classifier, and that will also come up with a particular answer or a particular result. Now, combining the results of both, it will try to make a consolidated final prediction. And this type of technique, it's called late fusion technique. Now, typically, when we talked about that person recognition system, right? In most cases, the person recognition system is an example of a late fusion technique, where we might have one type of network which is completely relying on the vision part and making a prediction based on the vision part or the vision modality. And there is another type of network which is, let's say, completely dependent on the speech part. And based on the speech signal that it's obtaining or it is able to capture, it will again give us some type of classification. And the final prediction result that comes out of the model, it's more or less like a combination of both, and then it tries to predict the final results. So that is an example of late fusion. But for this particular session, when we are going to talk about image captioning, we are going to see the early fusion mechanism, where we are going to get the different types of modalities like speech, text and vision in this case, or images in this case. We are going to have the specific representation or the feature vectors created from both the modalities. And then we'll do a combined or a joint training. And out of that, we'll have the final classification. Okay. So basically, these are like different styles. And depending upon the type of the problem, we will go with either of these approaches, or our choice of this approaches might vary. But overall, in terms of, for the image captioning problem, in most cases, it is the early fusion technique, which is widely adopted. Okay. Now coming to this specific problem of image captioning. What exactly is the image captioning problem? And, what are the typical use cases similar to this where we might even apply such a particular problem? Okay. So the image captioning problem was actually became more popular when there was actually an image captioning task or a competition which was created, and there was a data set which was published. And this is again the same COCO data set, which has like data set related to multiple such image related problems. It is, be it object detection, image segmentation, key point detection. So these are different types of problems that can be solved using the COCO dataset. But image captioning was also one of the key problems which was given. The main idea was in that particular dataset, especially in the training dataset, we would be getting a set of images and the corresponding caption that best described the image. So I think in the original dataset, we have like 5 captions for each image. And that's how we'll be getting the particular data set. Now, the idea or the goal is to train a particular model so that it's robust enough. And whenever a particular image is fed into the model, the resultant output of that particular model would be a textual sentence which best describes the particular image or the particular data set. Okay. So that's the main use case or the problem that we'll be talking about. And one of the key problems in the initial approaches of the particular image captioning problem was explainability or the interpretability part that we talked about. Now, sometimes, let's say, and again, like both image and text related problems requires a huge amount of data set, and depending upon the volume of the data with which we train the model, the final results actually varies. So the initial results of such a technique was not so good, and especially the captions that were obtained, and it is actually mentioned in the, I think, the main paper of the entire encoder-decoder approach that we'll be seeing later. So anyways, like there, the results, the initial results of such an approach was not that good enough, although the final, the caption or the output that was coming of the out of the model did make sense. It was like a valid English sentence, but still, like, it was not able to capture the key points within the data. And that's where another group of researchers went on to understand that why is it so, or why exactly is the model giving such a result? Can we even bring further interpretability into it? And that is where more modern techniques of image captioning came into picture, where certain attention-based networks were used within the model, and it would help us to understand the key areas within the image based on which the model would be giving the final textual output. Okay, so that's how we are going to see the visual attention technique, which will help us to even understand that whatever the model is kind of predicting, why is it saying so, like by looking at certain portions of the image. Okay, so this is the image captioning problem in general. Now, before going deeper, I just wanted to discuss about the entire approach of encoder-decoder architecture. And again, like some of you might be already aware of it, but I just wanted to make it much more simpler for everyone to understand so that they can follow the remaining part of the session. Okay, so in most cases, an image captioning problem, since it involves multiple modalities like both text and images, it is always recommended to go with such an architecture which can kind of combine the main features of both the images as well as the text data. So one such example is an encoder-decoder architecture. So typically, let's say if we are working or dealing only with images, in a particular encoder-decoder architecture, the encoder part would look like a conventional convolutional neural network, where we would have the main data passing through a set of convolutional layers with certain activation functions. And then we'll have certain pooling layers, which will kind of downsample and pick up the main important features out of it. And we will have a layer of such networks or layers, basically, to get a final a latent space vector or a feature embedding. And typically in any classification based algorithm, once we have that final feature vector, it goes through a layer of classification networks, say maybe a fully connected layer, or maybe any other network for that matter. And then it kind of gives the final classification result, right? Like that is how a normal conventional convolutional neural network looks like. But in an encoder-decoder architecture, like till the latent space vector, it remains the same. It is part of that encoder layer, where the convolutional layer and the non-linear layers or the activation functions kind of helps us to understand the key features or representation from the main data. And then we use a set of pooling layers that kind of downsamples and kind of picks up the main or the major important features that has maximum weightage. And then it goes through a series of such networks, right? So this remains as a part of the encoder layer. Now, the main important thing here is the decoder layer. So the decoder layer kind of performs the reverse of what the encoder does. So in this case, instead of convolution layer, we have something called deconvolution layer, which means that from those output feature maps, it tries to get the useful and the lower dimensional features and then converts them into little more higher dimensional representation. Okay. And similarly, instead of pooling layers, we have something called unpooling layers, which means that instead of downsampling the main, the feature information, it kind of upsamples it. Okay. So finally, out of the decoder layer, we expect the main image or the original data to be reproduced. And depending on the typical, the loss function or the cost functions, we can understand that how well the decoder is able to recreate the input which is being passed to the encoder. Okay. So this is a kind of a classic example of an encoder-decoder architecture. And again, like whenever we deal with problems such as maybe image denoising or maybe image coloration, so in those cases, encoder-decoder architectures are very popular. And even for dealing with text-related data, right, for any machine translation or any sequence-to-sequence modeling, these kind of encoder-decoder architectures are quite popular. Okay. Now, the reason I brought the point of encoder-decoder architecture is because whenever we go for an image captioning problem, in most cases, and as we talked about the joint representation and the early fusion techniques, right? So in most cases, the encoder part is actually a convolutional neural network, which will consume the main image. It will go through those layers of convolutional neural network and create the final feature vector. And based on the feature vector or the representation that it generates, then it passes the final output to the hidden layers of a RNN-based decoder network. So in this case, in the encoder part, it will be a convolutional neural network, whereas in the decoder part, it is a recurrent neural network. And why recurrent neural network? Because since we are dealing with text data, right, which is a sequential data, that's why we go for a recurrent neural network in this particular case. Okay. So the main idea is we will get those specific set of features from the image itself and pass that into the hidden layers of the stack of LSTM or long short term memory, right, which is an example of an RNN based network. So it goes to the hidden layer of that, and along with that, it supplies during the training process the initial set of captions which are available, and it goes through certain a word embedding process because it needs to convert the exact text data into something as a vector representation or a particular embedding value, right? And then it passes that through the network. So the main combination or the fusion process happens at this particular step, where each word embedding value is being combined with the main feature vector values from the particular input image, and then it goes collectively through the set of here, like for this example it is LSTM layer, but for any RNN layer for that example, and it goes through a sequence of that, and finally it tries to predict the final words as a result of the particular the training process that it goes through. Okay, so the outcome of the model would be a complete sentence that would best describe the particular image that is involved. Okay, so these are again like some initial set of approaches in which convolutional neural networks are used as an encoder, and recurrent neural networks are used as a decoder for solving an image captioning problem. Okay. Now, I'll go through some of the modern or advanced technique as well. But before that, let us even try to understand the entire idea of an attention mechanism. And particularly, we are going to talk about the importance of having the visual attention mechanism that would give us much more better results and much more robust result. Okay. Now, what exactly is the attention mechanism? So an attention mechanism is nothing but the entire idea of it is based on that within the entire data, only certain points of the data are more important and has the maximum importance or weightage towards the final classification or the final task that the model is supposed to solve. Okay, so that's where the attention mechanism comes in, which kind of selectively concentrates on only few relevant features or values, and then tries to assign certain weightage on top of the importance of it. Okay, so basically it's like the entire data set is not that much important in terms of the final results that we want to draw from it, but rather it is just certain portions of the data that has the maximum importance, based on which we will come up with the final result of the model. Okay. So this is the fundamental idea of the attention mechanism. And again, the attention network or the attention mechanism is one of the key ideas of more modern, transformer-based architectures. And I would, in fact, like highly recommend all of you to go through these papers. So the first one talks about the entire idea of an attention mechanism. And the second one actually tries to apply some of the ideas from this particular paper into the transformer architecture, which I think the authors have primarily applied on text-related data, but later, like people have even applied transformer architectures for vision-related problems, or even for multimodal related problems where multiple modalities are involved. Okay. And just one more point to add on this, like in the entire attention mechanism, attention can happen at two levels. One is the global attention model or the mechanism, and the other one is at a local level, local attention mechanism. Now, particularly for an image classification problem, the main idea is to see at the local portions of the image, but at the same time, maintain the entire global information that it wants to draw from that model. Okay, so that's why this attention mechanism actually helps a lot, which tries to relate the final outcome of the model with some of the local observation, but at the same time, it tries to conserve the entire global information of the main input data that it will take. Okay. So this particular approach involves something called visual attention mechanism. And why visual attention mechanism? Because like here, from that entire image, first it will go through certain layers where, based on certain portions of the image, it will then make a decision that what is the next word it's going to be. Okay. Say, for example, when it starts with a particular image and the feature encodings that feeds within the model, and then with when it tries to predict the particular result, it tries to look that what can be the next possible prediction that can happen based on the image value itself. Okay, so let's say if the first word is the single letter A, and then considering the image, what can be the next main important part of it? So here it kind of was able to pick up the entire dog portion of the image, and that's where it said it kind of predicted the result as a dog. Okay, and then it goes to the next portion. Then it tries to go through multiple layers of understanding to find the typical action or typical other portions within the image, basically, to find out that whether whatever that it will be predicting would actually make sense or not. Okay, so the attention network would actually come up with such matrices, or let's say certain values, which will have higher weightage in only some portions of the particular image. And based on this weight vector or weight matrix, but whatever the way we term it, it kind of goes along with the decoder and then try to make the final, I mean, the next output that it wants to drive from it. Okay. So typically, this is the result of the attention network. So the attention network comes up with a particular weight matrix in which, as compared to the entire matrix, only some portion of it will have higher weightage or higher weight values. And using those weight values, the particular model would try to predict the next possible or next probable sequence that can happen. Okay, this is the entire idea of this visual attention mechanism, and this particular paper actually talks about it in much more details, and they only, the authors only came up with this entire idea of visual attention, and they even discussed that how exactly visual attention was trying to solve the problem of looking at certain local features and then trying to predict the final, the possible outcome of the model. Okay, so the entire, now like bridging everything together, along with a conventional encoder decoder model, we try to have an attention network which tries to improve the final results of a model. So here we will have a set of images which is being passed to an encoder network, which kind of generates the encoded feature vector. And for each, the entire feature vector is passed as different hidden layers. And previously we saw that the values directly went into the RNN or the LSTM layers, but in this case we will have another set of attention network in between, which will try to look at different portions of the image, and then based on the importance of certain region, it will pass those importance or those extra weight values to the decoder or to the LSTM networks, and then as a combined result, the model would try to predict what is the next possible sequence that can happen. Okay, so the upgraded or the advanced form of a particular architecture to solve an image captioning problem is this particular one, where we will still have an encoder CNN, but the decoder RNN will have an attention network, which will help us to get much more reliable and much more robust results. Okay. So again, just to highlight some of the key benefits of the entire attention-based model. So the attention-based model tries to select various parts of the encoded feature or the main image, and then tries to highlight the most relevant portions of it and assigns more weightage to those specific pixel values. Okay. So it tries to ultimately convey that only certain portions of the image or certain pixels are more important than the others. And that's where the attention networks allows the network to look at different portions of the image and produce much more better results as compared to a conventional encoder decoder model. So it tries to consider the local aspects or the local contextual information of the entire image and then tries to produce the final output result. Okay. And as talked about, like the previously the paper that we have seen so far, right? The visual attention mechanism actually has the major importance of this particular approach. So it is a particular technique which tries to interpret that how the object detection encoder network can produce certain targets based on which the final results would come in. Okay, so it tries to even highlight those specific portions of the image which has those maximum weightage towards the final result which the model would be telling. Okay, so typically for any image-based model, whenever we go for any deep learning based approaches, right, in order to bring more interpretability, we go for something like class activation maps or certain heat maps that we create on top of the image, which tries to highlight some portions of the image which has more weightage, right? So the idea is kind of similar here as well, but the only thing is the weights are decided not only based on the image part, but at the same time along with the textual input or the captions that are initially fed during the training process. So considering both these modalities, it tries to highlight or adds more weightage to those specific pixel values, and this kind of helps us to understand that why exactly the model is telling based on whatever the result that it gives. Okay, so say for example, in this case, based on this image, it tries to predict a caption of a man is riding a bike in the woods. Okay, and the main reason why it said that, it kind of highlights that through the image itself. So if we see, when it talks about the first letter of A, it kind of highlights only one specific spot within the image from where it was able to detect that, okay, there is only one object of interest within the image. Okay. And then when it talks about a man, it kind of highlights only the man portion of it. Okay. Then it tries to understand that within this region, or by looking at this region, I'm thinking, or the model is rather thinking, that it is actually a man. Okay. And then when it talks about riding a bike, if we see, it kind of covers mostly around the man and the bicycle position. So here, when it talks about the bike, it kind of highlights only the bike area and not the man area, right? So looking at maybe the wheel or the front portion of that bike, it is kind of telling that it is actually a bike which is there in the image. So that's why it kind of highlights, or kind of gives attention to those only specific portions of those image. Okay. And similarly, when the remaining part about it is like in the woods, right, it kind of highlights everything outside the man and the bicycle. It kind of highlights the external portion of it, and from there it kind of says that maybe the remaining portion of the sentence is related to like in the woods, like basically looking at the surrounding or the external environment related position. Okay. So this is a very good interpretability technique that kind of comes along with the entire encoder, decoder, and attention-based network, right, for an image captioning problem. And it kind of tries to highlight the key idea, or tries to explain that why exactly the model is giving such a particular result. But in case like if anyone else of you is like more interested to know about different types of model explainability can be brought into different areas or portions, I do have one I had taken the previous session, and maybe like you all can take a look at it. This might also help you to understand that why exactly model interpretability is so important, especially when we deal with unstructured data like images and text. Okay. Now coming to the next portion about model evaluation. Now let's say when we have the model results, or whatever the model is predicting as a textual data or a textual sentence, how exactly do we evaluate that the model is actually doing good? Or what else can we do to understand that maybe the model is not exactly giving the results that we had initially expected? Okay, so that's where some of these matrix comes into picture, which is slightly different from conventional convolutional neural network or any recurrent neural network related problems or approaches that we have seen commonly. So that's where like understanding these model evaluation matrix for an image captioning model is also important. Okay. Now, some of these techniques are quite commonly used for solving some text related data, like related to machine translation or any sequence to sequence modeling, right? Some of these matrices are popularly used, but there are like some specific matrices which are used for an image captioning problem as well. Okay. Now, the first and the most popular one, I would say, is this bilingual evaluation understudy, or BLEU, which is popularly known as. So this BLEU score is actually a popular metric which is used for machine translation problem, where it tries to compare between two different sentences, and based on the geometric mean of the main n-gram precision model that we have, or the precision score that it generates, it tries to assign some sort of penalty to the to the specific result. So it means that like within those the sentences that we will have, right, and let's say the sentence between the target sentence and the input training sentence that we will have, if some of those words are completely different in terms of the positional values as well, it will assign some sort of penalty to it. So based on the final scores, it will kind of tell that if the scores are high, then that means the model is quite efficient in terms of giving the final caption predictions as a result. Okay, so typically BLEU is something which works really well whenever there is any short sentence which is involved, but for longer sentences it actually is not that good, and it is particularly useful when true positives are more valuable over false positives. So whenever there is a exact maybe match between some of the words, and if that exact match has a higher weightage, then in such cases BLEU is actually a pretty good matrix. And as I said, like popularly it is actually used for a lot of NLP based problems, particularly around machine translation, or maybe converting a particular language from one form to another, and so on. Okay. Now, another popular metric, and most of the competitions or most of the popular image captioning frameworks are actually trying to push towards the CIDR metric, which is nothing but consensus-based image description evaluation. So this is a particular metric which is meant or designed for image description generation related problems, and it tries to find a certain similarity score between image description of the the reference sentence, which will be fed during the training process, along with the candidate sentences, and based on that it tries to consider a particular similarity. So it may not be a direct mapping between the words, but let's say even if there are certain similar words which are used, right? So based on that it tries to assign a score, and the final score kind of tells us that how good is the image description that is being generated. So image captioning is nothing but an image description approach, right? So it kind of helps us to understand that. So in most cases, what I have observed, CIDR is a pretty useful and an important metric that is widely adopted for such image captioning related problem. Okay. Now there are other two metrics which is also quite popular and well used. So one of them is called ROGUE, which is nothing but recall oriented understudy for gesting evaluation. So the ROGUE is almost like similar to the way the BLUE works, but the main fundamental idea is around recall scores rather than precision scores. So in BLUE it kind of considers the precision related scores, but in ROGUE it kind of considers the recall related scores. Okay, so basically this is also a very popular metric which is used for document summarization, and most of these metrics are related to any natural language processing, understanding, or generation related problem, because like the output of the particular model is nothing but a textual sentence, right? So that's why like most of these metrics are related to such problems as well. Okay. Now one good benefit of this ROGUE metric is that like it works really well whenever the sentences are longer, and it tries to measure the true positives over the false negatives. So sometimes it does lead to inaccurate caption evaluation, because in most cases, if you think about it, image captions are like one liners or one sentence which tries to highlight the main information within the image. So it normally doesn't have longer sequences, and often trying to understand true positive over false negative may not be a right particular approach when we talk about image captioning. But many people have actually used this, and sometimes it can be, this particular metric can be used to tune image captioning model to a great extent, depending upon the type of the data. Okay. And finally, we are going to talk about this Meteor metric, which is another popular metric used in machine translation, and it considers the harmonic mean of the precision and recall. So it considers both precision and recall, and it tries to keep the balance between the importance of like true positive over false positive as well as false negative. Okay. So Meteor kind of fails to understand some of the semantic similarity, but whereas some of these other metrics, like particularly CIDR, is actually better. And typically when some of the common words are actually have like lower frequency or like have scarce or any like distorted distribution, in such cases Meteor is not that good. But as compared to ROGUE, I would say that since it considers a balance between the precision and recall, it is sometimes like much better. But out of these four metrics, my recommendation would be around CIDR, because CIDR is actually especially designed for image captioning related problem. And otherwise, I have also seen that BLUE is also a one popular metric which is used in most of the papers and most of the research work around image captioning and some related problems around it. Okay. So that's mostly it about the entire image captioning problem. But there are like a lot of other similar application which is based on the same fundamental idea with maybe some changes around it. Okay. So some of the common or the popular applications in which such a an encoder decoder with an attention network can be used to solve similar problem is like, one of the ones is like, let's say, visual question answer, where we will get certain images, and from the image, if we ask a specific question, it will try to give a particular answer to it. So this is also a very interesting application, and this is where like a similar approach or a similar multimodal technique is used. Okay. Other such applications are, let's say, automated image tagging or image annotation, where people are trying to come up with generic frameworks which can help us in creating automated tags or maybe even annotations around it. So particularly when we go for any object detection or object segmentation problem, image annotation can be really a costly and a challenging process. And especially like depending upon the quality of the annotations that are generated, the final model results or the model performance would also matter a lot. So that's where people are trying to explore multiple techniques or multiple approaches which help them to do something like an automated image annotation, so that the entire cost or time of annotating or manually annotating image samples or data is kind of reduced to a great extent. And companies like Facebook and some of the other social networking platforms have this feature of automatic image tagging. Like based on the image itself, it will scan and go through it, and then it will try to highlight that small portion of it and try to automatically tag, saying that this image may belong to this particular category, or maybe we have so and so person who is there in this particular image. So these kind of automated image tagging application can also rely on such an multimodal deep learning process, which involves encoder-decoder mechanism. Okay. Visual description for visually impaired is another important application, and visual description is kind of similar to the image captioning problem. And another type of problem which some of the social networking platforms like Twitter or Facebook are currently working on is on this hateful meme detection. So sometimes people create, especially in the social networking sites, right? People create certain memes which might have sarcasm involved or some hateful content which is involved, right? And these social networking platforms are trying to come up with automated ways to either filter out the content or maybe temporarily block such contents until further validation. So that's where hateful meme detection is another similar application which involves a multimodal data set of images. But in this case, along with the images, the textual information may be written or kind of inscribed within the image. So in such a case, getting that direct textual data might be a little difficult, but considering techniques of OCR or any other similar techniques from where the textual information that can be extracted from the image can be applied, and then the remaining part of the problem remains almost like similar, where we can go for an encoder-decoder architecture and even apply a attention-based network to understand whether the particular meme or the image which considers the meme content is actually hateful, or maybe it is meant for maybe a lighter cause or something which involves some comedy into it. Okay. So that's mostly it regarding some similar applications. And I would highly recommend all of you to go and take a look at Google's AI conceptual captions competition, which is on a larger data set. And at the same time, I think like Google AI uses CIDR as one of the important metrics. And whatever we have discussed so far would be highly useful if you want to attempt such a captioning or a conceptual caption generation problem. Okay, so I would highly recommend all of you to take a look at this particular competition. Okay, so that's mostly it. This brings us towards the end of the session, and probably I'll open the floor for any question answer. And if some of the the concepts that we have talked about, if you're if you did not get a chance to understand it in depth, feel free to reach out to me through LinkedIn, or even you can drop an email to my email address, and feel free to ask these questions. Okay, so that's mostly it. So I'll open the floor for Q&A now.
Yeah. Thank you so much, Aditya, for such an insightful session. I feel like, a lot of people thoroughly enjoyed learning from it. There are a couple of questions as well from the chat. I'll pick those. And a couple of people asked about the slides. So please don't worry, guys. We'll take the slides from Aditya after the session and share it with all of you over the email, and we'll post it on YouTube comments as well. Other than this, Madhuri asked one curious question. What are the use cases of deep learning like that Aditya has worked in pharma industry, and how is it impacting the people in real life right now? If you could, throw some light on it, Aditya.
Okay. So typically in pharma industry, there are like multiple use cases, especially if we talk about certain use cases around drug related scenarios, right? deep learning is popularly used for understanding some of the key drug properties. And even recently, if you have heard about the Google's DeepMind team, right? They came up with the AlphaFold model, and even they published actually a particular data set which helps you to understand the protein folding problem. So the protein folding problem is again a pretty complex problem, and when like without deep learning, when this particular problem was approached conventionally, it used to take like multiple years to just solve this particular problem, where a lot of physical experimentations were involved, lot of high-end equipments were used to understand the protein structure and what formats it can unfold into. But this is a very important problem which the Google's DeepMind team was able to solve, and this helps us to even accelerate the process of maybe drug discovery, then drug screening, and suggesting new molecular structure that can happen or that can fuse with some other compounds or components involved. So these are some of the high-end use cases which are being actively looked into. But there are other common problems related to the pharma world, which may even involve around the manufacturing process as well, where certain whenever like high-end pharma products are developed, right? It may not be the actual drugs, but it can be certain devices or containers or components which goes along with the drug. So in those specific cases, maintaining the quality of the product is very important. So that's where deep learning models, which take in maybe the some of the images scanned from such environments and tries to understand if there are any defects around with it or not. Or when we talk about certain chemical components or chemical compounds which are involved in making a particular product, understanding the chemical signatures of a particular product is also important, because often what happens, there are certain industry standards or quality standards which are kept, which even ensures that a certain proportion of a chemical compound should be there. But if that proportion goes beyond a particular limit, it might not be recommended for a particular drug component or a drug compound, right? So by just looking at those specific devices or those specific products, it gets very difficult to understand whether it is actually meeting the quality standards or not, or maybe it is contaminated with some other particles or other components. So that's where certain equipments like hyperspectral cameras, which can actually look at products from different electromagnetic wavelengths and capture those signals, are used. And using those signals, certain deep learning models are fit into, just to understand the chemical properties or the electromagnetic spectrum signature that it captures, right? Is within the particular range or not, or whether it is kind of exceeding that. So that's where these kind of use cases also comes into picture. And apart from that, there are like, whenever there is involvement of any text related data related to any let's say any medical journal or any such publications which are involved, or even I think if you are aware of the entire clinical trial process, where multiple clinical trial studies are conducted depending upon the different use cases. It can be related to drugs, it can be related to devices, and some of the the human factor research which are done during the process, which is often published through FDA or some of the other regulating bodies. So even in those cases, deep learning is heavily involved for extracting some key information out of the data, and later it helps us to understand the overall the macro trends that happen around the pharma world. Say for example, let's say a particular type of drug is being kind of administered in different use cases, or maybe a particular type of medical condition is being administered, and specific records related to it is being noted down. And using these deep learning model, it helps us to understand the global trend around the entire pharma world. Okay, so there are multiple use cases. It completely depends on the type of the data, and like typically what I have observed in the pharma world, data related to let's say natural language processing or NLP related problems is quite high as compared to the image or vision related problems. But when we talk about the quality standards or the manufacturing process of a particular pharma product, that is where image related use cases are heavily involved. And whenever there is unstructured data, deep learning techniques are quite efficient as compared to conventional machine learning processes. Okay. All right. Any other question?
Yeah. There are a lot of thank you messages coming in, by the way, from Hafsa. She says, thank you for giving this valuable opportunity. She loved the session. Red hearts. Couple of more thank you messages. I think people really loved the session, and the way you presented, they thoroughly enjoyed it. Thank you so much for that. More questions. Some of the people have asked about the implementation bit. So maybe if you could share some maybe if you have some resources at top of your mind, any repo or anything through which they can refer to to learn about the implementation.
Right. I'll quickly show one inference part. Again, the training part is something which will take some time to develop, but I do have the specific code repository related to it. So for the inference part, it's pretty simple. We would have to just use the trained model and then feed a particular image to it, and then it will scan through the entire image and would come up with a caption like this. So these are some of the results we have already seen. Let me probably try to zoom in properly. Yeah. So these are some of the results that we have seen. For the training part, it's little time consuming because since it involves a lot of data, and especially the COCO data set is quite large. And from the data, a lot of pre-processing steps are also involved for both the images and as well as for the textual data part, right? And especially when we deal with text related data, the cleaning and the pre-processing steps is quite heavy. Especially if there are certain stop words within the data or certain words which doesn't have a higher frequency, right? It's always better to neglect those words. Otherwise, the model output is often have bias towards the certain words which have higher frequency or higher count within the data set itself. So definitely, I do have the implementation code and everything. I'll probably share, but I would highly recommend all of you to go through some of the papers that I have suggested. The paper actually talks about in details the necessary steps that is needed. But yeah, definitely, I'm going to share the code and everything so that anyone, if they want to take a look at it, they can definitely try the hands-on part of such a particular image captioning problem. Okay.
Cool. Yeah, a few more questions. Someone asked, can you please elaborate on how we can image annotate by multi-modality, since we can only have one modality to my understanding in an annotation. If you can maybe brief about it.
Yes. So in such cases also, let me probably show that image that we had, right? So even for image annotation, the data set for training a particular model would involve two modalities, both the images as well as the corresponding textual information when we are initially training it. The main difference between image annotation and a particular image captioning problem is that in this case, the main subject of that sentences would be highlighted. Say, for example, when we talk about this image, here we will have a man and maybe a bike involved in it, or maybe the external surrounding, which is the woods around it. So what the model would do, it will try to pick up these relevant weights and it will try to identify the specific position or the coordinates of these pixel values. So the final outcome of that model is not only the label of a man, but at the same time, the specific XY coordinates around the man. And if we are going with something like a polygon representation, it will have multiple XY values of that annotation region. But if we are going with something which is like a rectangular annotation, right, it will have specific, in most of the cases, it is the top corner of the rectangle and the coordinate related to it is given along with the height and width of the bounding box. Okay. So typically that would be the output of the model, the main subject, the specific title associated with it, and the specific coordinate positions or maybe the pixel positions of that image. And it will prepare that as maybe an annotated JSON or any format that we talk about, and that would be the final output. But overall, it is kind of same, but it is like one more layer on top of it, which tries to understand the relevant subject and the object within the particular textual information and the region around it, and highlights the coordinates of that image around it. Okay.
Madhuri asked a follow-up question based on when you shared about your expertise into the pharma sector and your work. She asked how do you manage to generally get the subject matter expertise as a DL researcher, apart from the technical expertise, if you can throw some light on it.
Okay. Again, like it kind of depends on the type of problem and the projects that we are dealing with. In terms of the expertise, like as and when you get to work on a particular problem, the way I usually do it, I try to understand the theory part of it as well. So I try to go through some of the state-of-the-art research work that has been published around that area. What are the work that is already done, and some part of it can be reproduced or not, and what are the typical open-ended question which is often mentioned in most of the research works. So from that, I try to pick up those points and try to apply on my own as well. Now, again, like one thing related to the pharma world is the domain expertise that comes along with it. Like even if we know a lot about how to apply a deep learning method or any machine learning method for that matter, and even if we know how to deal with the particular data set, but it is the domain expertise or the domain knowledge that is something which we try to pick up while working on a particular project. Say, for example, I talked about the clinical trial studies, right? And even I talked about some of the specific drug-related concepts. So that's where, like, even I had to acquire that specific domain knowledge. And especially like when we were dealing with some of the molecular data sets, right? Those were given in specific, canonical forms or smile structures, which is often, used in the molecular world. So even understanding or kind of, refreshing the initial knowledge on chemistry and molecular biology was needed to work on those problems. So that domain expertise is something which goes hand in hand along with applying some of these deep learning methods. And I would say the final outcome of such deep learning or any AI models in general depends a lot on the domain knowledge itself. So if we know about the entire domain or the type of the problem that we are going to solve, and then translating our understanding of the problem into something which the business stakeholders can interpret or can understand and easily accept, is something that goes along with experience. So once you start working on those scenarios, I'm quite sure you will be also able to pick up those relevant domain related knowledge or domain related experience, and then try to apply the same in translating whatever the model is telling into something which the end users or the end business stakeholders can easily understand. Okay.
Awesome. Yeah, I think like one final question, which I want to personally ask from you.
Yes.
What is like the one piece of advice you'd like to give to all the community learners out there, who just got started with deep learning and want to dive deep into it?
Okay. I think the best advice that I can give is to get all of your hands dirty in working with actual problems related to it. And as and when you deal with different types of data sets and different type of problem, for every problem you will learn something which is unique only to that particular problem. So, and again, like even if you go through a lot of theory around deep learning or a lot of maybe research paper, if you come across, or if you try to study across it, until and unless like you actually work on these problem hands-on, you might not get the best exposure. And applying machine learning and deep learning to a problem may not be that difficult, considering some of the robust frameworks of TensorFlow or PyTorch that we have, and there is like abundant material around it of how to apply such techniques or such model. But until and unless you actually work on those problems, you won't be able to make something which is more useful or more reliable for any organization or any business for that matter. So applying machine learning and deep learning model can be easy, but the outcome that you might be getting might be good, but may not be good enough. So in order to get that extra edge, or to generate results which are good enough and much more helpful for the final organization, that I would say only comes with practical exposure and practical experience. So that's where, like, whenever you come across any particular problem which you see that like has been solved using deep learning, try to approach those problem hands-on. Try to get the data itself, try to apply the model and see whether you can improve the results or not. And if you're trying to refer any particular online source or maybe any particular research paper, maybe the first step would be to reproduce most of the results that are mentioned in the research paper. So if the results are good enough, and if you're able to successfully reproduce the result, this would even give you the additional confidence of trying to explore something which has not been explored. So maybe trying out with certain other hyperparameters, or maybe trying some different type of modeling techniques or different flavors of architecture within your particular approach, right? So these kind of confidence or additional ideas you will get. So just to summarize, I think the best advice that I can give is to get your hands dirty and work with different data sets and type of problem in which you'll be able to apply some of these deep learning methods and architectures. Okay.
Right, right. Thank you so much, like, for such an elaborative answer. And like, once again, thank you so much for taking out the time and like, taking such an insightful session. We can clearly see, like, from the thank you messages that community thoroughly enjoyed learning through it.
Yep. And thank you for giving the opportunity, by the way.
Yeah. I think, yeah, that's pretty much. Thank you again to everyone who joined in. Wish you all a good day ahead. Have a good day ahead. Bye-bye.
Yep. Thank you. Thank you.